Welcome to a screencast on acid-base equilibrium. This will finish up the handout from class on Wednesday. This is page 4 of the handout. And we'll start with an example of a 0.1 molar aqueous solution of propylamine, which is C3H7NH2. It has an equilibrium hydroxide concentration of 7.24 times 10 to the minus third molar, and tells us what that pH is. And the question is to find the Kb value for propylamine. Now note, we have a number of things, including a reasonably high OH- concentration, a pH that's above 7, a Kb value, and then the structure of propylamine looks like this. Some carbon hydrogen region of the molecule, and then this is an amine, so it's kind of like ammonia, and with, instead of 3 hydrogens bonded to it, 2 hydrogens and then some carbon stuff over here, and there's a lone pair, which makes this a very good proton acceptor. So we have a lot of things that indicate we're dealing with a base. Now, to determine the Kb value, given the data that we have, we're going to do some calculations and an ice table and the usual type of thing. And then just as a note, here's kind of a visualization of what's happening. Here's a propylamine molecule. It's surrounded by lots of water. Here's a water molecule that it might interact with. And how the interaction might occur is the water gives up or donates a hydrogen to the propylamine. Then it makes the C3H7NH3+, and the water leaves behind an OH-, and it looks something like this. So here's the water getting near the propylamine, near the nitrogen, and a hydrogen is taken from the water, leaving behind an OH-. So this is a base dissociation of water, and there's the equation for it. And then our ice table, and again, our initial is we're going to pretend that we had a 0.1 molar solution with no dissociation. And then the change will be the dissociation that, of course, occurs. And that gives us at equilibrium, kind of our standard things, the concentrations in terms of the change x, and then our Kb value, of course, will be given by the expression shown here, usual equilibrium constant type expression, and B stands for base dissociation, of course. And then, since we have a known concentration of OH-, so this is essentially how much the propylamine has dissociated, we know our value of x. So we can plug that in for the C3H7NH3+ concentration, for the OH- concentration, and for the remaining propylamine concentration. And there are our values. And there is our base dissociation equilibrium constant of 5.7 times 10 to the minus fourth. So it's a weak base, partially dissociates water. Now, as a note, we've done acid equilibrium type calculations. We've now done base equilibrium calculations. And there's a lot of similarities, but there's some differences. And acid and base equilibria are similar in many respects, but they're kind of opposite because acids and bases are chemically kind of opposite to each other. So how do we link the two? How do we link acid and base equilibrium situations? And it turns out that water can act as both an acid and as a base. The term we use is we say water is amphoteric, or it's amphiprotic. It can donate a hydrogen ion, or it can gain a hydrogen ion, donate a proton, or gain a proton. And another way of saying this is that water autoionizes, at least a little bit. Even in pure water, some water molecules will dissociate, making H3O+ hydronium ion and OH- hydroxide ion. And the equilibrium constant expression for this is Kw, where W stands for water, and that's equal to H3O+ concentration times OH- concentration, And the value of this is 1.0 times 10 to the minus 14th. And that's if we're doing things at our kind of standard 25 degree Celsius. Now, of course, what this means is if here's our water mixture, pure water, out of every about 10 million water molecules, one of them will do that. So one water molecule will end up dissociating, losing an H+. That H+ is grabbed by another nearby water molecule, so we have an OH- and an H3O+, and the rest of the water stays as intact molecules. Now it's worth noting that in a neutral solution, H3O+ concentration is equal to OH- concentration. But in an acidic solution, H3O+ concentration will be larger, OH- will be smaller, and the reverse for a basic solution. And this product at 25 degrees Celsius will always equal 1 times 10 to the minus 14th. And here's a picture, a different way of looking at what's happening to water molecules. And they dissociate. One of them dissociates, leaves behind OH-, and then the H+ is grabbed by the other water molecule, making hydronium. We have conjugate acid-base pair, where water functions both as a base and as an acid. So water is autoionizing, water is functioning both as base and as an acid, and this relationship allows us to, if we know H+ concentration, determine OH- concentration, and vice versa for any given solution. And then, of course, pH and pOH can also be related as well. And here is a chart showing some, kind of representative substances, some that are acidic, some that are basic, and some that are reasonably close to neutral. The H+ concentration and the pH that corresponds to that. And then the OH- concentration and the pOH, which is the negative log of OH- concentration that corresponds to these. And notice that as the H+ concentration gets smaller, the OH- concentration gets bigger. The product of the two is always 1 times 10 to the minus 14th. And then as the pH gets bigger, the pOH gets smaller, and the sum of those is always 14. So pH is negative log of H3O+, pOH is negative log of OH- concentrations, and in general, the relationships are H3O+ times OH- is 1 times 10 to the minus 14th, and pH plus pOH is equal to 14. And these are useful because they link acid and base, and they allow us to do analysis and calculations with either acidic or basic solution, kind of interchangeably. So for our last example on this screencast, we have a 0.01 molar solution of hydrochloric acid, and we'd like to determine the concentrations of the hydronium ion, the hydroxide ion, and the pH and pOH values. And we'll start with what we know, which is HCl is a strong acid, so it fully dissociates. So if we have a 0.1 molar solution of HCl, we get 0.1 molar H3O+, fully dissociates into hydronium or hydrogen ion. Well, if we know H3O+, we can calculate OH-, and solving the Kw expression for OH-, it's equal to 1 times 10 to the minus 14th over H3O+ concentration. That's 1.0 times 10 to the minus 14th over 0.010, which works out to be 1 times 10 to the minus 12th molar for the hydroxide concentration. And notice, of course, acidic solution has a much higher concentration of hydrogen ion than of hydroxide ion. And then pH is the negative log of H3O+ concentration, which is negative log of 0.01, which is 1 times 10 to the minus second, which is, of course, 2 or 2.00 with the correct number of sig figs. And then pOH is negative log of OH- concentration, so we can take our hydroxide concentration and take the negative log of that, and we get 1 negative log of 1 times 10 to the minus 12th is 12, And then, of course, the other way we could have done this is to say, well, pH plus pOH adds up to 14. If pH is 2, then 14 minus 2 gives us a pOH of 12. And that does it for finishing up the fourth page of the handout from the lecture class on Wednesday the 17th. And that ends this screencast.